Okay, hi everyone. It's my great pleasure to introduce our very own postdoctoral research fellow of blockchain at UBC, Mina or Dr. Bagheri. Ho Hopefully my pronunciation is okay. Dr. Bagheri received her PhD degree in mathematics and computer science from Tehran Polytechnic, and I believe her PhD research topic was focused on lattice-based and code-based cryptography. You can even see from here, right, the collection to the post-quantum cryptography. After that, she had research positions at Sharif and the Institute for Research in Fundamental Sciences, IPM, in Tehran, kind of doing right, like both theoretic and applied cryptography research. Of course, her research work spans post-quantum cryptography, in particular, lattice and code-based cryptography, and very recently, right, some interesting like new design focusing on blockchain systems. Because right after she joined our blockchain at UBC, and she tried to apply like those like post-quantum and like information like theoretic techniques to design right the so-called quantum resilient solutions for right not only blockchain systems but also maybe healthcare, right, or like a government or like a banking systems at large. To me, it's one of the most exciting time. Why? Like in the past, like maybe several weeks or like a few months, we have waitlist, right? Many like very exciting breakthroughs and achievements in the quantum world. So I personally believe that right, this is one of the best time to translate some fundamental research into real world solutions, right? To kind of prevent potential quantum attacks. Because if we are not ready, right, when the attacks indeed happen, maybe it's too late. So that's why, right, with this, and we will learn like Dr. Bagheri, right, will kind of walk us through from some like fundamental knowledges, maybe to some like cutting edge directions. I'm very looking forward to her presentation. The floor is yours, Mina.
Thank you so much, Dr. Fink. Thanks for the introduction. And thank you, everyone, for being here today. Today, we are looking at the status of post-quantum cryptography standardization and how it will fundamentally reshape blockchain security over the next few years. Yeah, we will move from the high-level threat of Shor's and Grover algorithms into the building blocks of blockchains and examine case study of Bitcoin and Ethereum and conclude with the urgent roadmap for migration. Modern cryptography faces two distinct hammers. The first one is Shor algorithm, that this is the destructive one. And with Shor algorithm, we have catastrophic break for public key cryptography. And because a Shor algorithm solves integer factorization and discrete logarithm in polynomial time that breaks RSA, Diffie-Hellman, ECDSA, and EDDSA that all are the core of blockchain authentication. And the second one is Grover algorithm that makes a quadratic speed up on hash search. And with this algorithm reduces security of symmetric primitives by half. For example, for two 56-bit hash, under this algorithm, we have 128-bit security. So hash functions remains viable under this quantum attack and quantum algorithm, but with reduced margin. Okay. I think all of you heard about Q-Day, but let me explain what is Q-Day and when is the Q-Day. Q-Day is the moment when a quantum computer becomes powerful enough to break classical public cryptography like RSA, ECC, and Diffie-Hellman in practical time. So after Q-Day, TLS certificates, code signing keys, and blockchain signatures can be forged. VPNs and secure messaging become breakable, and software updates can be spoofed, and identity and authentication systems collapse. And indeed, Q-Day is the point where this mechanism become commercially viable. So um, um, before Q-Day, the quantum threat is harvest now, decrypt later attack, where the attacker collect encrypted data today and can be decrypt them once Q-Day arrive. Oops, I think. And now we want to know how far away is the Q-Day. Let me walk you through this timeline because it shows how quickly quantum computing is progressing and why Q-Day is no longer a distant concept. On the left side of the image, we see the machines with noisy physical qubits that are not yet capable of breaking cryptography. These systems are significantly important, but they pose no threat to RSA and ECC. As we move forward, the curve begins to be upward. This is where improvement in logical qubit here in logical qubit construction started to compound. In this curve, 3 years stand out: 2025, 2031, and 2035. 2025 is the time that multiple research groups like IBM, Google, and several national labs are expected to demonstrate a stable logical qubit for the first time. And this is important because logical qubits are the foundation for scalable quantum computation. And this is another important time because Michael Mosca estimates that RSA 2048 will be break with half chance in 2031. And this is just 6 years from now. This doesn't mean every blockchain break instantly in 2031, but it means the capability becomes feasible. And because the attackers are already performing harvest now, decrypt-later operations, the damage begins before 2031. And we can see the amount of logical qubits that we need to break RSA 2048, that is about 4,000 logical qubit, and for ECC is about 1,000 logical qubit. They are large numbers, but we are still a significant distance from that. But the expectation is a large scale fault-tolerant quantum computer could be operational by around 2035. So it means that by 2035, the world must already be quantum safe. And U.S. government mandate transaction to quantum resistant cryptography by 2035 to address national security risk. So if we see crypto standards here, all public key crypto standards are vulnerable to attacks from quantum computers, and symmetric key crypto like AES and SHA would also be affected by Grover algorithms, but less dramatically. So we need to find cryptographic algorithms which are secure against attacks by both classical and quantum computers, the area that's called post-quantum cryptography. And the core primitives in this area is digital signature and quantum safe. Digital signature and quantum safe can, since they underpin secure communication. In 2016, National Institute of Standard and Technology, or NIST, initiate its post-quantum cryptography standardization process, marking a proactive response to the anticipated impact of quantum computing. Research in post-quantum cryptography has been active for more than 20 years, and multiple quantum safe candidates are now being developed to replace RSA and ECC. Now you can see the research category in post-quantum cryptography. This category includes lattice-based cryptography, code-based cryptography, multivariate cryptography, hash-based signatures, isogeny-based cryptography, and MPC in the head signatures. Each family differs in security assumptions, efficiency, key size, and maturity. And among them, hash-based signatures rely on minimal and conservative assumption, and they well understood, long-suited, and robust against quantum attacks. So, but typically, hash-based signatures have large signatures and just suited for high assurance environment. And lattice-based cryptography has a strong security foundation with excellent performance and versatility, and efficient key exchange and signatures, and widely adopted in NIST PQC standards. And they have good balance of speed, key size, and implementation flexibility. And other PQC families add just diversity, because it is useful for defense in depth and avoiding single assumption reliance. So now we can see the NIST post-quantum finalist. Now we have standards for chem and signatures. We have two standards for chem, ML chem or crystal Kyber, which is lattice-based and is the primary standardized chem. And the second one is HQC or Hamming quasi-cyclic, that is code-based and chosen to complete ML chem with a different hardness assumption. And we have three standards for signature: PQ standard for signatures, MLDSA is based or crystal dilithium, SLHDSA or Sphinx Plus, and FNDSA or Falcon. And now we can say about blockchain. Let's begin by breaking down the blockchain itself, its core component, and how they interact and why they matter for security. We know we have two quantum algorithm that will be affect on blockchain. And Shor algorithm will break the signature, and we know signature in blockchain is equal to ownership. So if private keys can be derived from public keys, wallets can be drained, validator and miners can be impersonated, and transaction can be forged. So the impact is sudden and total. We have total collapse once it is visible. And with Grover algorithm, the impact for blockchain system with this algorithm, proof of work difficulty shifts, faster search will be available, and lower collision resistance and potential fairness and distraction in consensus. Now we want to know about signature in blockchain. Here, I want to show you about the comparison between PQ signatures versus classical signature. Summary of sizes and the time, verification time and signature time. As you can see in the table, dilithium is fast but has large key size and signature size. And Falcon has compact signatures but is expensive, and it has expensive key generation. And Sphinx Plus is extremely slow and has very large signature. Now we want to know suitability of these PQ signature standards for Bitcoin. As you can see in the tables, cost of replacing ECDSA with dilithium, if we replace the ECDSA with dilithium, since the dilithium signature is 2.4 kilobytes, and for ECDSA is 64 kilobytes, about 40 times bigger. And dilithium has fast sign and verification and large transaction overhead. Falcon has the signatures. Falcon signature is about 650 bytes, and that is good as compact signatures. And but it has expensive key generation. And Sphinx Plus signature is about 8 to 50 kilobytes. So very conservative security, but it has very conservative security and is impractical for blockchain. And post-quantum security, we can say, is achievable but not size neutral. Why this is important? Bitcoin migration isn't just a mass problem, it is logistical one. Our time-bound estimates show that even with 100 network bandwidths, migration the entire UTXO set would take months. And Bitcoin's decentralized nature means there is no central authority to force this upgrade. And so, in the UTXO model used by Bitcoin, we aren't just updating a balance. We are managing a massive set of individual digital coins. So, the challenge for post-quantum migration is that we have to move every single one of these millions of UTXOs to new quantum safe addresses, which is a massive logistical hurdle that could take months or years. And you can see here for full migration, we need about 55 to 75 days at minimum. And at realistic bandwidth usage, we have need many months to years. So even if the perfect post-quantum signature existed, Bitcoin still cannot migrate fast. So because every UTXO must be spent and resigned. So this is the effect of replacing post-quantum signature in blockchain, in Bitcoin. And how about if we replaced it in Ethereum? Ethereum faces dramatic storage and call data expansion when switching to post-quantum signatures. Because if we compare it with ECDSA signature, the signature size for ECDSA is 64 byte, but the dilithium is about 40 times bigger. And Sphinx plus signature is more than 10 kilobyte. So since Ethereum pays gas per byte, large signature directly translate to higher cost. Okay, now we want to know about Ethereum execution time. Some post-quantum schemes are fast to verify, but is slow to sign. For example, the lithium has balanced performance based on this table, but Falcon is has extremely slow key generation, and Sphinx Plus is has very slow signing and unusable latency. So signing latency directly affects wallets, validators, and rollups. We've seen that post-quantum cryptography signatures are a performance nightmare. They are 40 times larger and significantly more expensive in gas. So how does Ethereum survive this? The answer is account abstraction. Standard Ethereum accounts are dumb. Their security is hard coded into the protocol. But account abstraction turns your wallet into a smart contract. So this gives us crypto agility. That means we don't have to wait for a dangerous network while hard fork to upgrade everyone's security. And more importantly, it solves the cost issue through signature aggregation instead of every user paying for a giant 2.4 kilobyte signature on chain. A bundler can collect about 100 transactions, verify them off chain, and submit a single compressed proof to the mainnet. In short, account abstraction is the bridge that allows Ethereum to move from the weak ECDSA area to the post-quantum area without crashing the network performance. If you want to know about large growth impact on Bitcoin and Ethereum, post-quantum migration can increase blockchain storage by 2 to over 40 times based on this table. And storage growth is a hard scalability limit because storage affects node decentralization, synchronization time, historical verification. And fully automatic migration would destroy lightweight nodes. And we need selective opt-in PQ adoption. Now we want to know about consensus in blockchain. Proof of work security rely on hash pre-image resistant and honest majority of hash power. With Grover algorithm, it has the effective security of hash functions. So faster block discovery, we have faster block discovery for quantum capable miners, and it increased centralization pressure. So proof of work is weakened but not broken by quantum computing. About proof of stake under a quantum attack, we know for proof of stake security assumes private keys are unforgeable, stake ownership is cryptographically enforced. So with since Shor algorithm breaks ECDSA and Schnorr signature, it allows private key extraction. So as a consequence, validator key theft, stake takeover, and long range and history revision attacks. So proof of stake fails catastrophically without post-quantum signatures. About BFD, we know BFD relies on a fixed set of validators voting to finalize blocks. And the weak point here is each vote is secured by a digital signature like ECDSA and Schnorr. And with Shor algorithm can derive a validator's private key from their public key. So once a key is derived, a quantum attacker can cast votes as if they were a legitimate node. So a quantum attacker can reach the supermajority threshold, usually 2/3, without controlling the physical hardware of the node. Because a BFD usually involves a smaller well-known list of validators, it provides a concentrated attack surface. And an attacker doesn't need to break millions of users. They only need to break the keys of one third or half of the validators to halt or fork the chain. So BFD consensus suffers from severe fragility due to its absolute reliance on signature-based authentication. A key finding, here is the proof of work is resilience, but proof of stake and BFD are fragile. And if we look at the existing side of consensus, we move from simply patching Bitcoin to reinverting it. Um, so now we want to know about quantum solution for consensus. Here, quantum proof of work is the industry answer to the energy crisis. And quantum proof of work replace classical hashing with quantum sampling problems like boson sampling, and its advantage is energy efficiency because classical proof of work is energy intensive, because miners need guess and check nonsense. But here this consensus uses quantum hardware to solve sampling puzzles, potentially reducing energy consumption by a factor of 1000. And this kind of consensus is Grover proof, but the current status is still largely centralized in research and requires specialized photonic quantum devices to function as nodes. Quantum version of proof of stake utilize quantum entanglement and quantum measurement for validator selection, and and it uses quantum entanglement to ensure that validator selection is perfectly random and impossible to hack. So if you break a quantum proof of stake key, the no cloning theorem actually prevents you from making a usable copy of the validator's power. But the performance of these consensus is good because it can achieve extremely fast block times with millisecond confirmation and offers unconditional security. And about quantum version of the BFT, in this consensus utilize entanglement and quantum teleportation, and the advantages are higher resilience because classical BFT can handle up to 1/3 malicious nodes, but QBFT can theoretically handle up to half. And it has faster finality because QBFT can reduce communication rounds, and it has unconditional security too because offers that is physically impossible to intercept. We talk about QBFT, but the reality is a scalability barrier. These are not these kind of consensuses are not ready for deployment to run QP proof of stake. For example, every node in this room would need a quantum memory buffer and dedicated fiber linked to every other node. Until we build a global quantum internet, post-quantum cryptographic running on the classical computer we'll have today is our only practical shield. So now we want to see the impact of quantum threat on a smart contract. The smart contracts are the most dangerous risk, and many have hard-coded addresses. And if the network moves to a new post-quantum address format, those contracts fail and assets are permanently locked. So the quantum impact on a smart contract, one impact is unauthorized access and asset theft. And because attackers can bypass signature verification and ownership of contracts can be hijacked, allowing authorized withdrawal of funds and modification of contract logic. And the second impact is breaking privacy, preserving contracts. And contracts usually utilizing ZK snarks or other privacy protocols based on discrete logarithm and become with quantum threat they are become transparent. So confidential data and shielded transaction can be unmasked by quantum attackers. And with quantum threat, we have invalidation of hard-coded addresses because many contracts contain fixed addresses for payment receipts or external calls. And if the network migrates to a post-quantum address format, legacy hard-coded addresses will fail. So as a consequence, asset may be permanently locked in dead contract. So as a result, significantly higher gas cost and a slower transaction processing with post-quantum cryptographic. The last quantum impact. With replacing the signature with post-quantum one, since they have larger size, signature size, we will have significantly higher gas cost and slower transaction processing time. So what is the migration strategy for smart contracts? It's better to adopt NIST standards and move toward standardized PQC algorithms. Use hybrid signatures, and that means implement a transition phase where both classical and PQ signature are required to ensure worst case security. And shift from procedural code to logic-based language, for example, answer set programming or ASP, and enhance to enhance the ability to mathematically prove contract security and reduce exploitable bugs. And use ZK Stark instead of snarks, because Starks are generally considered quantum resistant as they rely on hash function rather than trusted setup or discrete logarithm. And use verifiable delay functions to prevent attackers from using quantum speed to manipulate leader election or time-sensitive contract outcomes. This slide represents the core risk assessment of our survey. We are broken down exactly what happened to every skate holder when we finally pull the trigger and replace ECDSA with post-quantum signature. As you can see, the impact isn't the same for everyone. I want to highlight three critical areas of severity. Here, the inactive users, a smart contract. Where is that? Here, a smart contract that this one is high, and yeah, this one that is fragmented L2 ecosystem. If we want to see here for inactive users, can see this row. For active user, migration is just a software update for active user. But for inactive or cold wallets, the risk is catastrophic. Blockchain nodes cannot distinguish between a legitimate dormant owner and a quantum attacker trying to drive that old key. So if these users don't move their funds before Q day, the phase is silent and permanent loss. And if we want to see a smart contract, where is this? Yeah, here. A smart contracts and hard-coded addresses. This is perhaps the most dangerous row because as we see many smart contracts have payment addresses hard-coded into their logic, and if the network shifts to the new address, PQ address format, those hard-coded links break. And the contract might execute perfectly, but it will send funds to a dead address format. So, and another one is fragmented L2 ecosystem. Layer 2 system and bridges rely on off-chain signing. If a mainnet upgrades, but L2 side chain doesn't have the resource or the community support to follow, those bridges become the weakest link. We risk a scenario where the L1 is safe, but the entire L2 economy is drained through its legacy bridges. This table shows that post-quantum migration is less a cryptographic replacement problem and more a large-scale coordination problem. Where inactive user multi-signature setup and a smart contract pose the greatest risk of irreversible asset loss. In this slide, my goal is to show post-quantum migration is not replacing just ECDSA with post-quantum one. We must also rebuild the entire ecosystem of advanced cryptographic primitives that use in blockchain systems. Blockchain relies on advanced signature primitives, as you can see in this table, not just standard signatures. For example, we have multi-signatures that multi-signature, threshold signature, ring signature, blind signature, and adapter signatures. For example, multi-signature and threshold signature are backbone of institutional custody and bridge security. The quantum challenge here is size. If a standard PQ signature is already 2.4 kilobyte, a multi-signature for a group of 10 people becomes a massive data burden for the chain. Ring signature and blind signature, they are about focused about privacy. The ring signature and blind signature allow for anonymous transaction. The problem is that current PQ versions of these are extremely inefficient. And moving to quantum safe privacy today often means sacrificing almost all network performance. An adapter signature, about this signature, there are invisible glue for the lightning network and atomic swamp. And these signatures allow transactions to happen off-chain or across different blockchains. As of today, PQC equivalents for adapter signatures are still in the early research phase. So while NIST has standardized basic signatures, we don't yet have a standard efficient signature. And we call these kind of signature exotic signatures. We don't have a standard efficient exotic signatures. This is a massive research gap that the industry must fill if we want to keep features like lightning and privacy alive in the quantum area. Why this signature matters? Because multi-signature used in valid and threshold signature used in custody, consensus, validator control, ring signature used for privacy, and block signature used in privacy preserving payment, and adapters and signature is core to lightning network and atomic swap. Let's take a look at who is actually building post-quantum blockchains today. It is interesting that every real project in this space still runs on classical hardware. So none of them rely on quantum networks, and they rely on post-quantum cryptography to secure classical blockchain. QRL or hash-based, which is based on hash-based signature, is the most mature example. Algorand and Cardano are actively researching PQ-ready consensus. Komodo has experimented with dilithium integration, and Bitcoin PQ and PQ fabric explore lattice-based signatures and PQ proof of work variants. The key observation is that these projects are not quantum blockchains. They are classical blockchain hardened with post-quantum cryptography. And that's exactly the direction the industry is moving: practical, incremental, and deployable today. When we look across this project, three design patterns emerge. The first is post-quantum native chains. Blockchain built from scratch with post-quantum signatures as the default. This offers a strong security, but often struggle with interoperability and adoption. And the second pattern is hybrid or transitional chain. These systems support both classical and PQ signatures, allowing gradual migration. And they maintain backward compatibility but introduce more complexity. And the third pattern is research driven integration. This is where mainstream chains like Ethereum, Cardano, and Algorand explore PQ upgrades, but with long timelines and conservative deployment strategy. Across all three patterns, the trend is clear. Post-quantum security today, forever, clean slate or hybrid designs, not fully quantum systems. Now let's talk about the more protocols like quantum blockchains. These schemes promise stronger security, better randomness, and even unconditional guarantees using entanglement and quantum communication. But in practice, they face enormous barriers. And most quantum blockchain proposals suffer from O&2 communication overhead, meaning they become unmanageable as the network grows. And they require quantum memory, which is extremely fragile and short-lived. And they depend on global quantum network that simply don't exist today. For example, we have these quantum blockchains here that this one has a strong theory but high overhead. This quantum blockchain has limited attack resistance, and Rajan and Banerjee, and they have a heavy quantum resource and need heavy quantum resource use. So quantum blockchain sacrifice scalability for theoretical security. So where does this leave us in 2026? We can group the current landscape into three categories: post-quantum blockchains, that classical blockchains secured with post-quantum cryptography. These are deployable today and represent the most practical path to forward. And the second one, hybrid blockchain. This system combines classical and PQ components. They are transitional and experimental, but they allow gradual migration. And fully quantum blockchain, this remains theoretical. They require quantum network, quantum memory, and infrastructure that is still many years away. I don't know. Do we have
Yeah. So
more
maybe,
time or not?
yeah, maybe the previous slide was like a perfect kind of right, uh, concluding remark for today's presentation. So first of all, right, thanks a lot,
You're
Mina, and for
welcome.
your presentation. It's very informative and like it contains right many interesting concepts and knowledge, and it's comprehensive, right? Kind of, I still remember the big table. Instead of looking at one item, you have a comprehensive list of items, and then, right, trying to understand the impact. This is very important, in my opinion, for companies who would like to do post-quantum migration, right? Sometimes it's not as simple as just replace the signature. Definitely no, right? So this is maybe the biggest message I've learned today. If right, when it comes to the real post-quantum migration, at least two things. Number one, you need to understand all the components of your
Exactly.
system, right? And the second, like you will have like different choices, like a hybrid, like here, right? Hybrid or fully quantum or mostly kind of PQ cryptography, right? How to choose one, right? That fits best to your company. Sometimes it's more than the technology. It's also about the logistic, right? Other things and so on. So this is uh, kind of, in my opinion, like it sets up the right mind model to think about this problem, right? It's not just a new technique or a, a new like component. No, it's more than that. And we need a comprehensive understanding and we need a systematic thinking. So,
Mhm.
right, I think this will be so important. It's not like just writing a paper or writing a survey, right? It's all this like engineering approach and the cryptography approach that will play an important role, right? For this, I want to thank our speaker one more time for right kind of introducing this like framework, this like mental model when it comes to this quantum safe blockchain design. I believe right similar mind model can be applied even to traditional sectors such as right financial institutions and government organizations and so on. Yeah, maybe for the sake of time, we can only have one at most one quick question. Yeah, any quick question from our audience? Yeah, seems no. And now, finally, right, let's thank everyone, in particular our speaker, and to our uh, future audience who will watch this recording, right? If you have any questions, feel free to reach out to me now. I think, right, you can quickly Google search her contact information. Yeah, thanks
Okay.
everyone, and see you next time. Bye
Thank
bye.
you. Bye bye.